Hello, everyone. Hello. Waiting for some more people to join up. So, I was in Spanish class this morning because my Spanish class is period two, and I we were practicing like words for family members and also adjectives, and so I'm kind of ahead of the class, so I'm always saying stuff that like typing stuff into the chat that's like weird or saying weird stuff, and I don't think anyone even like Google translates what I say, so I've gotten more adventurous in what I'm saying. And so um, I typed into the chat. I was like, because we were talking about grandparents, and so I said, um, los abuelos son viejos a no ser que tiene teen mom, which means grandparents are old unless you have a teen mom. So, and then there's like no reaction because no one is even like looking up what I'm saying. So that makes me feel more emboldened to say more weird stuff in class. How many do we have now? So, okay, so let me talk about the final exam. Your final exam is available. You have 2 attempts, so you can take it once and see what you got wrong and try to figure out how to do those questions if you want to. You can take it twice. You get 220 minutes per attempt. That's way more than you're going to need. I wanted to set a time limit. I didn't want it to be an infinite amount of time, but a finite amount of time. So, you have uh, 3 hours and 40 minutes. I can't imagine it would take you anywhere near that much time. I'll take the higher of the 2 attempts. You can use notes. You're expected to work alone, though. You can use a calculator. Let's see. The final is 18 questions. It's approximately one half of the questions are from semester or triad 3. Then the other half, so it's like 25% triad 1, 25% triad 2, 50% triad 3, approximately. Okay, so that's the final. My hope was that this week some of you would be doing late assignments um, and getting caught up to improve some of your grades. If you are in that group of people who is doing late assignments and stuff, you need to send me a Canvas message by Wednesday, by the end of the day on Wednesday, telling me what I need to grade. Okay? If you don't tell me what I need to grade, I'm not going to look at the past unless you tell me to go back and look at the past and grade this stuff. Okay? And I need to know by Wednesday because that takes me more time to do than to grade other things. All right? It takes me much more time to grade late work. So, all right. Let me see what else there is. There's going to be no office hours next week because you're working on the final, so that's your independent thing. I will have office hours today, though. Let's see. So today I'm going to review basically through Triad 2 today. And then on Tuesday, I will review up through Triad 3. So everything will be reviewed by the end of the day on Tuesday. You might want to take the final before then, though, because Triad 3 is recent, so I would probably try to take it this weekend and see how you do. All right. So I'm going to go ahead and get started. So, first thing I'm going to review today. So, on Tuesday's lesson reviewed kinematics, forces, and energy. So I'm going to start off today by reviewing momentum. Okay. And so momentum is denoted by P, and it's equal to mass times velocity. So it's a vector, meaning that it has a direction. If you're going to the left, you have a negative momentum. If you're going to the right, you have positive momentum. Okay? The total amount of momentum that a system has is going to be P1 plus P2 plus P3 plus ... for however many objects are in the system. Okay? So the reason that momentum is so important is that in collisions, it is conserved. So the total initial momentum is equal to the total final momentum. Okay, so if we were to actually write that out, so what if you had, for example, a system that has two particles? Okay, then your conservation of momentum equation is going to be m1 v1 initial plus m2 v2 initial. So that's the initial momentum, mv plus mv, there's two parts to the system, equals m1 v1 final plus m2 v2 final. So so that's your general conservation of momentum equation for two particles. But one of the things we talked about was what is called a completely inelastic collision. And so for a completely inelastic collision, the objects collide and then they stick together. So because they stick together, they basically act like a single object with a single speed and a total amount of mass equal to the sum of the two masses. So your conservation of momentum equation in this case would be m1v1 plus m2v2 equals m1 plus m2, so they're acting as a single object, times v final. So in both of these equations, you can solve for whatever you need to solve for. In a completely inelastic collision, kinetic energy is lost. It is converted into other forms. In particular, it's converted into heat. Okay? So in a completely inelastic collision, kinetic energy becomes heat. And so let's suppose you wanted to figure out how much heat was dissipated. Well, what you would do is you would calculate the initial kinetic energy as 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So that's your initial kinetic energy. Your final kinetic energy, now remember these two objects have collided and stuck together, so now they're a single object of mass m1 plus m2 and final velocity vf, where you calculated the vf right there. And so then you would just subtract those two, and that would be the heat dissipated. Okay. We talked about this concept of impulse, which is denoted by J. And depending on the information that's given, you would calculate impulse in different ways. Okay. So if you're just given a force and a time, then impulse is force times the time elapsed. So this is the force that acted on the object. This is the time that that force acted for. So the force turned on, you pushed for a while, and then you turn the force off. You stop pushing. Another alternative is you have a force versus time graph, which maybe looks like this. And the area under the curve is the impulse J. So it's either force times time, or if you have a graph, it's the area under the curve. So why do we learn about momentum, or why do we learn about impulse with momentum? And the reason is that if we were to look at the impulse due to the net force, which would be, again, this would be the net force times the time elapsed, then the impulse due to the net force is equal to the change in momentum of the object. Okay, so impulse and momentum are connected to each other in that way. And there was also if we take this equation and we divide it by delta t, we get the sneaky form of Newton's second law, which was change in momentum divided by change in time equals the net force. Okay, so we use this to figure out the force during a collision. So if you have a video of a collision, you can figure out what the speed is before the collision and what the speed is after. So from that, you could get the change in momentum. And then the time elapsed, if you had like some ultra high-speed camera, you could actually figure out how much time that collision is taking, and then they bounce off each other. You could figure out that amount of time, and then you could use the sneaky form of Newton's second law to figure out the force of impact. Okay. Oh, hello, Hazel. Hello, Hazel. You be a donut hole. Are you a donut hole? Hmm? What do you do? What do you do, Hazel? What do you do? Hello. Hello, sweetheart. Okay, go back. Go back, you lump. Go back, lumpkin. Hazel! What do you do? What do you do? Silly Billy. Okay, turn around. So the next thing we talked about was circular motion. All right. So circular motion, you have some object that is moving in a circle, and that circle has a certain radius. And there's this thing called the period, which is the time it takes for the object to go around the circle. Okay? Now, as you are moving around the circle, your velocity is always going to point tangent to the circle. Okay? So, if you move to this location, then your velocity points over here. Now, if you recall, acceleration is the rate of change of velocity. So when you are moving in a circle, your velocity is changing not in size, but in direction. So that still counts as an acceleration. It's a change in direction. Okay? And so you have an acceleration. And it turns out that acceleration points towards the center. I can't prove it to you without calculus, but if you take my class next year, I will prove it to you. Okay? So that's the acceleration. So then we learned some equations for the velocity and the acceleration. So in particular, we learned that your speed, if you are moving in a circle, is 2 pi r divided by the period. So that equation comes from distance over time. The distance around a circle is 2 pi r. The time it takes to go around the circle is the period. The acceleration is called the centripetal acceleration. Oh my gosh. Oh. Boogers. Hey, Boogers.
What's up, man? What's up, boogers?
Whoa. Almost fell over.
What's up, boogers? What's up, dude? What you doing? What you doing, boogers? What you doing? See you later, man.
Okay, so the acceleration is called the centripetal acceleration. Centripetal means center seeking. So that's why it's called the centripetal acceleration, because the way the math works out, it always points towards the center. And so that is speed squared divided by radius. So to have a really large centripetal acceleration means that you're going in a really tight circle very fast. We could take the formula for speed and plug it in here, and we can get an equivalent equation for centripetal acceleration, which is 4 pi squared r over the period squared. So just like Newton's second law is valid for linear motion, it is also valid for circular motion. So we can apply it to apply Newton's second law to circular motion. And in this case, so for the acceleration, I would plug in mv squared over r. And then the force in this case is called the centripetal force. So the centripetal force is the force that makes you go in a circle. Oops, there should not be an r squared there. That should be v squared over r. And kudos to you if you caught it. I should give you a wolf buck if you caught that. That shouldn't have been r squared. It should have been r. So the centripetal force can be whichever force, any of the forces that we have learned about already. So it could be, a friction force, could be gravity, it could be elastic force, could be normal force, any of those forces. So this equation is used pretty much as is for what is called a horizontal circle. So a horizontal circle is one where, the plane of the circle is level with the ground. Okay, so horizontal circle problems are really quite simple. But then, kind of the more complicated circular motion problem is what is called a vertical circle. Okay, and so a vertical circle, the reason it's more complicated is because, okay, here's your circle. So a vertical circle is like this, like a Ferris wheel. Okay, and if you're at the top of and the thing about a vertical circle is gravity is always going to be a centripetal force. Okay, if you're at the top of the vertical circle, gravity points down. If you're at the bottom of the circle, gravity still points down. So you see how gravity kind of like is pointing towards the center of the circle part of the time and away from the center of the circle for the other half of the time. Okay. Typically you have a second force involved. You have to have a second force in vertical circles because here there is no force pointing towards the center. It's pointed away from the center. So why would it curve up? So there has to be a second force present up towards the center of the circle. And you may or may not have a second force at the top. Your acceleration, if you're at the top of the circle, is going to point down towards the center. And if you're at the bottom of the circle, your acceleration is going to point up towards the center. Okay? So what would Newton's second law look like in each of these cases? Well, if you're at the top of the circle, then your net force is up force minus down force, so F minus mg. Okay? And that would equal minus mv squared over r. So why is that a minus sign? It's because the acceleration points down in the negative direction. If you're at the bottom of the circle, your net force is still up force minus down force, F minus mg equals, then we have an upward acceleration, so that's going to be plus mv squared over r. Okay? So then we went on to talk about gravitational fields. Gravitational fields. And so gravitational field is another word for the acceleration due to gravity. Same thing. So the gravitational field of the Earth is 10 newtons per kilogram. Okay, so acceleration is measured in meters per second squared, so you obviously can use meters per second squared. But typically when we're talking about gravitational fields, they use the equivalent unit, newtons per kilogram. So the formula for a gravitational field is denoted by little g, and it is big G times big M divided by r squared. So big M is the mass of the thing creating the field. Because whenever you have a gravitational field, you have one thing that's making the field and another thing that is experiencing the field, okay? And that depends on the situation. So, if we're talking about, so in some contexts, big M could be the thing experiencing the gravitational field. So for example, if we were talking about the motion of the Earth in the gravitational field of the Sun, then big M would be the mass of the Sun. And little m, the thing that's experiencing that gravitational field, is the Earth. If we were talking about the motion of a satellite around the Earth, then big M is now the mass of the Earth, and the thing experiencing the gravitational field is the mass of the satellite. Okay? R is the distance from the center of big M, that mass. Okay? Big G is is a constant of nature, so it's going to be the same in every single problem. Big G is not the same thing as little g. Little g is a variable. It changes all the time. Big G is a constant of nature, and its value is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. One thing I wanted to remind you about is this R. Sometimes you have problems that deal with altitude. So if you have a planet, maybe the radius of the planet is little r. If we talk about the altitude, so maybe the satellite is up here, the altitude, we'll call it A, is the distance above the surface. So big R is the distance from the center, so that would be this entire distance right here. Okay, so basically we have that big R is equal to the radius of the thing plus the altitude above the surface of the thing. All right, so sometimes, so you got to be careful. You have to read the problem carefully. If it says distance from the center is blah, that's different from saying the altitude is blah. Okay. So then what we did is we talked about circular orbits. And so by the way, I'm forgetting one other thing. If we want to actually calculate the gravitational force, that's equal to little m times g, where little m is the mass of the thing experiencing the gravitational field, and g, little g, is the size of the field experienced. Okay? All right, so we went on to talk about circular orbits. So circular orbits, orbits of planets are in general not circular, they're elliptical, but circular orbits are much, 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 much simpler to analyze. So the way that we analyze them and the way that we analyze elliptical orbits is we use Newton's second law. Okay. For the acceleration, we use the centripetal acceleration, but we use that other form of it, the 4 pi squared r over period squared. And then the force, the centripetal force, is the gravitational force. So if you do some math on this, you can get Kepler's law, Kepler's second law, 2 of 3, actually, which says that G times big M times T squared equals 4 pi squared r cubed. So important point here, big M is the mass of the central body. Not the mass of the satellite. It's the mass of the central body. Okay? And so really there's 3 variables here. Mass, period, radius of the orbit. This is not altitude of the orbit, it's radius of the orbit. So that's radius of the planet plus altitude there. Okay, and so anyways, if you know 2 of these variables, you can solve for the third. So the way that I think this equation is coolest to use is if you are looking at something through a telescope, so you're looking through a telescope at this thing, maybe a satellite, you're looking at a satellite, you can see the satellite going around, okay? And so from that, you can determine the period. Also, you're looking through a telescope, you can see if it's a small orbit or if it's a big honking orbit, okay? And so from that, you can determine the radius of the orbit. So if you know the period and the radius, you can solve for the mass of the central body. So this equation is how things like planets are weighed, because you can't take a planet, pick it up, put it on a scale, okay? So anyways, that's my review. On Tuesday, I will review rotational dynamics, and then that'll be a complete review of the